Hello everyone, my name is Pablo Rotondo and I'm going to be presenting our joint work with Florent and Koechlin. So we are both from the Université Gustave Eiffel in France. And the title of the article and the talk is Absorbing Patterns in BST-like Expression Trees. So let's see what this is all about. So an expression tree is a decorated or labeled tree where internal nodes correspond to operators and leaves correspond to either variables or constants. So here we have a logical expression, a regular expression, so here there's the clean star, the concatenation, and the plus, which is the union, and an LTL formula. So these expression trees could be used as inputs for algorithms. And here we're interested in producing random expression trees, which then can be used for the purposes of automated testing or benchmark testing. So once you have a random procedure to produce these expression trees, well, the question is the distribution you get realistic? Is implementation simple? And finally, do we have some kind of theoretical guarantee as to the resulting distribution? And here, in this work, we'll be considering the case of BST-like trees. So in BST-like trees, we fix a target number of nodes for the tree. So for us, the size is going to be the number of nodes. So that's internal nodes plus leaves. And to present the algorithm, I'm going to give this pseudocode that appears in a tool for LTL formula. So to get a random formula with n nodes, if n is equal to 1, then we just draw a random leaf. If the size, the number of nodes is 2, then we must pick a unary operator for the root, and then the child is again a random leaf. In the general case, we must pick a random operator for the root, which could be now unary or binary. If the root corresponds to a unary operator, then we produce the child recursively by the same procedure, which is now of size n-1. And in the binary case, we must also decide the number of nodes that correspond to each child. So how do we do that? We pick the number of nodes uniformly. So a BST-like tree looks a bit like this. That's a typical shape. And BST-like trees are not uniform among trees with n nodes. And in fact, a uniform tree has a very different typical shape. This is a typical uniform tree. And the difference comes from the fact that in the case of BST-like trees, when we have binary node, as we use the uniform to distribute the nodes between the children, each child has roughly n over 2 nodes. But in the case of the uniform trees, that's not the case. So there's a child that concentrates most of the nodes, and the other one which has just a square root of n nodes, roughly. And so this explains the difference in height and width for the uniform and the BST-like trees. But at any rate, the uniform distribution is also a very natural distribution because, firstly, it maximizes the entropy among all distributions over trees with a fixed number of nodes n. There are efficient algorithms for this, so at least these three that I mentioned here. And one can study it theoretically by counting, so analytic combinatorics. Now, in the case of the BST-like distribution, this distribution is used in automated checking of tools. And the reason for that, I think, is that for once, it can be parameterized. So the probabilities of the nodes and the probabilities of the, meaning the operators and the leaves. And it's very easy to implement and very efficient. So now let us see what happens first in the case of the uniform distribution. So in a previous work with Florent Koechlin and Cyril, we considered the uniform distribution, and we showed that there's a very simple reduction algorithm that if you take a very large uniform random tree and you reduce it, then on average the tree you get is of constant size. So that's very bad. And let's see a bit how the reduction works. So the reduction is based on the existence of a so-called absorbing pattern. So absorbing pattern P is associated with an operator, which here is the circle star, the absorbing operator. And if you have the absorbing operator as root, and one of the children is the absorbing pattern, then you know you can reduce the whole expression to P, so it's equivalent to P. So that's a very common thing. So for example, in logical expressions, any expression like this one that's equivalent to true is absorbing for the operator or, because or something or true is true always. Now, in the case of regular expressions on two letters, A plus B star is the language of all words, corresponds to the languages of all words. So this expression is going to be absorbing for the union, the plus. And lastly, of course, the 0 is absorbing for the multiplication. So this arises quite a lot. And for the case of regular expressions on two letters, in principle, the constant you would get for the theorem is of size like 3 million. So it looks like a lot, but adding a few simplification rules, we proved also that the constant can be taken down to roughly 80. So it's a bit problematic. So the uniform distribution has this flaw. And so in our work here, we wonder if the BST-like trees suffer from the same flaw. So we pick a random BST-like tree of size n, very large, tending to infinity. We reduce the tree using these absorbing patterns. So we reduce bottom up. And the question is the size at the end very small? And so here we prove that the situation is not the same because we have 5 regimes. And here I present the main 3 regimes in the case of regular expressions on 2 letters. So on the left, we have a linear regime, so meaning on the x-axis you have the size of your regular expression, of your tree, your n, and on the y-axis you have the size of the reduced expression on average. And so you see that that grows linearly, so there's not much of a reduction going on. In this second case, there's a sublinear regime, and there's a kind of strong reduction, but still the size after reduction tends to infinity. And on this last case, regime, we have a constant size. So this is a degenerated regime, as in the case of uniform expressions. And the other 2 regimes that don't appear here are transitional regimes between these 2 and these 2. So in this talk, I'm going to first review the model, then give you the main theorem and some ideas of the proof, and then with some conclusions. So here we just consider unary binary trees. So we have just leaves and binary and unary operators. And the BST-like procedure then depends on 2 vectors of probabilities, one over the leaves and one over the operators. So the procedure, as we saw before, is that the following. If the target number of nodes is greater or equal than 3, then we must pick the root according to the vector of probability for the operators. If the operator you get is binary, then you pick the children, the size of the number of nodes for the children uniformly. If the operator were unary, then you just produce the child with now n-1 nodes recursively by the same procedure. If the number of nodes were 1, then we would just pick a random leaf according to the probability vector for the leaves. And finally, in the case of 2 nodes, we are forced to have a root that's a unary operator, and so there we just consider the conditional probabilities among operators that are unary. Now, for the simplification procedure, the absorbing pattern, we must fix an operator, circle star, which is going to be our absorbing operator, and it must be of arity 2. Then we fix an expression tree P, which is going to be an absorbing pattern. And the simplification works bottom up, so it's from the leaves, and we work the way up. And each time we have a node that's the absorbing operator, and one of the children is P, then we reduce the whole expression to P. And what we are interested in is the number of nodes or the size after the simplification. And so we will denote the tree after simplification by sigma of t. So now we get to the main theorem. So we have an absorbing pattern associated to an operator of arity 2. We consider our simplification, which works bottom up according to the absorbing pattern and the absorbing operator. And we show that on average, so the expected size of a BST-like tree after simplification has fiber genes here, shown in this picture, according to the probability P circle star of the absorbing operator. So if the probability of the absorbing operator is less than 1/2, we have almost no reduction. So we have a tree with n nodes, and we expect on average the number of nodes of the reduced tree to be still linear. For 1/2, then there's a little reduction going on, so there's a log term in the denominator, but it's still roughly linear. And if we go a bit further up, we get to the sublinear case we had seen, and so there's like a square root of n, so there's a significant reduction going on. And then there's a second threshold, which depends also on the probability P1 of the picking a unary operator. And there, the size after reduction of a tree with n nodes is on average just log of n. And after that, we have a degenerate case, as pretty much as in the uniform trees. So we see that we have the whole range of behaviors from no reduction at all to the degenerate case. To show again the main regimes, now that we have seen our asymptotic behaviors. So the first plot here, the linear plot, of course, will correspond to the first case here. And there, the probability of the absorbing operator, which was the union, is 1/3. So we're definitely here. In the case here in the middle is the sublinear plot. We are in the significant reduction case here. And the probability of the union is just a bit more than 1/2. Finally, in the last case here, we are in the degenerate case. And you see that the probability of the absorbing operator is 8/10, which is, of course, more than 3/4, which is necessarily here. So let's look a bit at the details or the ideas behind the proof. So for the proof, we employ tools from analytic combinatorics. So our object of interest is going to be the ordinary generating function of the expected size after reduction. So here, T is a random BST-like tree with n nodes. We reduce it and we count the number of nodes. And so that's E of n, the expected number after reduction. And as is common in analytic combinatorics, we have two steps, the symbolic step and the analytic step. And here in the symbolic step, we find a formal equation which is going to describe the generating function. Here, that's going to be an ordinary differential equation. And then in the analytic step, we look at the generating function E of z, and the differential equation as analytic objects. And we use a so-called transfer theorem to translate the behavior of the generating function at its singularities. So that's the points where it ceases to be analytic, so where it behaves badly, into asymptotics for the coefficients, so our expected values. So that's the scheme, and let's see how we work out each step. So for the symbolic step, we need an auxiliary sequence, which is the probabilities of full reduction. So full reduction means that the absorbing pattern works its way up to the root. So we reduce up to the root. So the whole tree is going to be equivalent to the absorbing pattern. And so we call the probabilities gamma of n. And the formal equation we get is a differential equation, as I said, which has this form, so a first order differential equation, which will depend on the generating function A of the probability of full reduction. So it appears in the coefficient here, as you see. And well, the proof goes through a recurrence relationship because gamma of n, the probability of full reduction, come up naturally because the fully reducible trees actually correspond to a base case for the reduction procedure in a way. So if you have your reduced trees, your leaves could be original leaves or the absorbing pattern. And then for the analytic step, we look at this differential equation. So a first order differential equation, of course, can be solved explicitly. But the problem here is that the coefficients depend on an unknown generating function a of z. So to apply our transfer theorem, we need knowledge about this unknown generating function a of z regarding the probabilities of full reduction. And we show that the only singularity we must care about is z equals to 1. And so then we need precise asymptotics for a of z close to z equals to 1. And close to z equals to 1, we have that the solution of the ODE for E looks a bit like this, as that expression. And you can see that it depends on A, so the generating function for the probability of full reaction here and here. And so once we will get our precise asymptotic for A, we must translate them into asymptotic for E. So to get asymptotics for A, we have a similar procedure. So first we get a formal equation for the generating function. So here it's again a differential equation, but it's a Riccati differential equation. So it's not linear anymore. There's a quadratic term in A of z squared here. And the proof goes against a recurrence. It's a bit simpler than before, because a tree of n plus 1 nodes is completely reducible. But for that, the root has to be the absorbing operator, and then at least one of the children must be fully reducible. And so that's the recurrence, basically. And the good thing is that the Riccati equation can be turned into a linear equation, but of order 2 through a classical transformation, a classical trick. But the equation you get is of degree 2 now, so it can be solved directly. But anyway, there's lots of things that are known about linear ODEs, and in particular where they're analytic and the behavior at the singularities through what's called the Frobenius method. So with this, we get the asymptotics for A close to 1. So there are 3 cases depending on whether the probability of the absorbing pattern is less than 1/2, or greater than 1/2. And the nice thing about this asymptotic for A is that it also implies a result for the probability of being fully reducible. So the probability of being fully reducible tends to a constant, actually, which is positive, this gamma infinity, when the probability of picking the absorbing operator is greater than 1/2, and 0 if the probability of the absorbing operator is less or equal than 1/2. So when we saw the case of with no reduction at all, the linear case from 0 to 1/2, actually that corresponds to when there is no, the probability of being fully reducible is 0. And when the probability of being fully reducible is positive, it is this gamma infinity, then we start to see reductions in the trees. And so here we see experimental plot for the which corresponds to the probabilities of the third experimental plot we saw, the one with the degenerate case. And we see that this is the experimental average number of nodes that are fully reducible. And so we see it tends slowly but surely to the expected limit. And so now we get to the conclusions. So we have seen that BST-like expression trees have a wider range of behavior than uniform ones. So here we have a whole spectrum from no reduction at all to a degenerate case again. So one must be careful in how we choose the parameters, because there's a degenerate case. And for open questions of future work, well, a first question would be what happens if the absorbing pattern, absorbing operator, had arity greater than 2. So for example, A greater or equal to 3. Well, then we expect similar results, but the threshold should be 1 over A and not 1 over 2. And another interesting question would be, well, what happens if now we have several absorbing operators which interact between them? So that's the case, for example, of and or in logic. And so that's interesting, in particular in the case of LTL formulas, because of course the operators interact, and that's where BST-like trees are quite used. So with this, I finish my talk, and thank you very much for watching.